Excellent. Thanks, Toby. So good evening, everyone. So as Toby said, I'm the Principal Electrical and Systems Rolling Stock Engineer for RSSB. And I'm here to talk about the work we've been doing at RSSB on hydrogen, which has been supported by the whole of the rail industry, to be honest. And we've had great participation across the sector in actually developing this work. And it's an iterative process, as is everything we do at RSSB. So this is just the first publication of its kind on hydrogen, and hopefully there'll be many more. So the first thing I just want to cover is why are we even talking about hydrogen in rail? Why is it important? It's mentioned at a lot of forums. You hear about alternative means of powering rolling stock across the industry, and hydrogen is just one way of achieving the decarbonisation targets of the rail sector and all sectors in Great Britain. It's mentioned quite often in industry reports. So this is an example from a House of Commons Transport Committee report from 2021, which shows that it was important that battery and hydrogen technology play a part in decarbonising the rail network. And I would say that battery and hydrogen aren't the only solutions to decarbonisation. There are others out there. There is a group at RSSB set up specifically to look at those. It's called the Independently Powered Traction Working Group. They look at other fuels such as ammonia. So there is a lot of work going on in industry to try and decarbonise. And this is just some support we're giving to industry to help them go forward to look at hydrogen in particular. We do have a separate battery work stream as well. So what am I talking about when it comes to hydrogen on a train? Well, typically, as it stands, a train is powered by one of two means. So either by electricity. So the top in the blue, perfectly blue box, we either have DC 750 volt DC third rail or 25 kilovolt AC overhead contact line, which then powers the electric systems on the train. Or we have a diesel train, so external storage tank, fuel tank on board, powering an engine. It is entirely feasible to change that diesel tank on a train and actually have a hydrogen internal combustion engine. There are companies out there who have developed hydrogen engines, and you can use hydrogen as part of a fuel to an engine. So it doesn't basically provide the whole sort of fuel capability, but it can help in actually that combustion process. So if you take an ammonia engine, for example, so I know Nottingham University are looking at an ammonia engine. They use hydrogen and ammonia in parallel to actually for that engine to function. But typically, when we're talking about hydrogen in the industry at the moment, most people are actually thinking of fuel cells. And a fuel cell is essentially hydrogen storage on board. You then have a fuel cell which converts chemical energy to electrical energy. This is then stored on batteries on board, which then powers those classic electric systems which we've had for a long time. When it comes to actually looking at where this might be implemented in Great Britain, Network Rail, this is quite an old report. I think it was maybe 2018, maybe slightly later than that. This was called the Traction Decarbonisation Network Strategy, or TDNS for short. And it kind of shows where in the UK electrification is and where it's likely not to be in the future. And as you go through the report, it gives greater detail. So on the left-hand side in this particular image, it shows that potentially the Scottish Highlands could be a place where you could have hydrogen or alternative traction solution. Similarly, in the northeast, it's looking at sort of that area there, and there's it might be hard to see where we are now, but there are some lines on there which sort of show where you could use alternative energy. And moving forward, it also highlights Anglia as a potential option for this kind, and particularly Norfolk and Suffolk coast lines for hydrogen, and then Wales as well. But since then, there's been another report by another industry body, the Rail Industry Association. I hope I got that acronym right, RIA. And they've identified slightly different areas where hydrogen could be introduced. So it's, again, Scottish Highlands, the Northwest, and Wales, but it misses out the Northeast and Anglia. So it depends who's talking about hydrogen to where they think it could be implemented. So I think at the moment we could say it's feasible, just we don't know where from a whole industry perspective. So moving on, just looking at some of the work that RSSB RSSB has been doing on hydrogen. This isn't something that's particularly new. There's been quite a lot of R&D since 2005 by RSSB on hydrogen, starting with a feasibility study into the use of hydrogen fuel, the use of hydrogen as a traction energy store, and most recently, routes to entering service and future costs for hydrogen and battery power for traction. So there are reports available on the RSSB website in the research catalogue looking at actually how feasible it is to introduce hydrogen onto the UK rail network. And similarly, RSSB has been involved with some trials. So again, in 2005, 20 years ago, there was the hydrogen fuel cell trial by RSSB T722. And then in 2015, hybrid hydrogen fuel cell power pack trial. And then just mentioning some of the industry examples that are out there, and this is not all of them, but these are the ones that are widely reported in the media. Hydroflex by Porterbrook in 2018, and the Class 614 Scottish demonstrator in 2021. So hydrogen is within industry. People have knowledge on hydrogen, as you will hear later from Tom, who's giving an update from what work they've been doing on hydrogen at Evershot. But it's key to understand that this is something that's entirely possible. And often it's thought, actually, how can we introduce hydrogen in a safe way? And that's often the bit that the industry gets sort of stuck on. So that's where we've tried to help out. So we received a request from an operator to help with this, and it started really with a policy and standards review. Their specific request was to assess the adequacy of existing standards, determining the suitability and applicability of existing standards. My slide is frozen. And then understanding boundaries between affected parties, assessing the suitability of what's commonly called SRM, or the safety risk model that RSSB publishes to assess low frequency, high impact hydrogen safety events. And then looking at how we consider hydrogen in the context of against the operator's capability to apply a safety target of what's often termed ALARP, as low as reasonably practical. So these was the 5 key points from a request we received from industry. So in something's going on with my slides here. In 2022, we published a paper on this, which is essentially looking at what is the current state of hydrogen, what do we know, and what gaps exist in policy and standards. Covers quite a lot of detail. And again, this is free to download on the RSSB website. If you have to log in to download it, it's not behind a paywall. You just have to create a free login and you should be able to get a copy. It covers everything from standards to policy to boundaries of responsibility at quite a high level. But it's just an initial overview for us to understand, actually, is this really a problem that RSSB need to address? Understanding that we're member funded and we do things on behalf of the whole industry, not a single entity. So we need to make sure that actually this is going to be work that benefits the entire industry. So it covered quite a lot of content, and the outcome, unsurprisingly, was that there's a lack of significant standardization. Maybe we already know this, but it sort of proved that was the case. And from a policy perspective, this was one of the key questions that industry asked us, was actually what's our boundaries of responsibility? And when we're talking about that, that's in the context of if there's a hydrogen incident or accident, who's responsible and who needs to be involved to actually manage that incident, and who should be there and who shouldn't be there. So we sort of considered that in the policy paper. That gave us a good grounding to move forward to what is our most recent publication on this work. So this is enabling hydrogen for the rail industry by supporting safe decisions. And it started with colleagues in the RSSB policy team having quite a significant review of legislation and standards. If you're not familiar with the scope and force of rail standards in Great Britain, it's quite significant. There's a lot of them, and it can be complex to understand their applicability. Starting at the top, we have UK specific legislation. So this is things like the Health and Safety at Work Act, for example, or the control of major, or COMA as it's often called, and I'll come on to that shortly. I can't remember the acronym stands for, apologies. We then get on to the bit more rail-specific legislation if it's in scope of a project. So NTSNs, common safety methods, and national technical rules. And as you move down the list, compliance becomes less compulsory towards voluntary adoption. And there was a review of all these different types of standards and legislation. When it comes to UK-specific legislation, these were all the primary and secondary legislation that was reviewed. I'm just going to focus on a couple of those now, though, which is the Control of Major Accidents Hazards Regulations 2015, often called the COMA regulations, which is about quantities of dangerous substances in a single location and how you manage them. And in addition to that, the Planning Hazardous Substance Regulations in 2015, which is also plays a part here when you're talking about large quantities of hydrogen. It's important to realise that when we're talking about hydrogen trains, it will be quite a large quantity of hydrogen that can be stored at any single site. So colleagues in the RSSB policy team tried to simplify the regulations by making an applicability calculator so industry could understand, actually, does this really apply to you? Do you need to think about them? So using the calculator, you could click onboard storage, and that will bring you up this front page where you can put in the kilometre range of a vehicle, the maximum onboard capacity of hydrogen, whatever that might be, and the vehicle's fuel economy. Click go. And then it essentially bans the regulations. So if a vehicle, and I think it zooms in momentarily, but essentially if a vehicle falls into the dark green category, which is, so it's average distance in kilometres of a journey along the top, and down the side it's the fleet size, so the number of trains in the fleet. If it's in the dark green category, the PHSR regulations apply. If it's, no regulations apply. In the light green category, it's PHSR regulations. In orange, which is that quite wide band across the middle there, that's PHSR and COMA Tier 1. And in the red in the bottom corner, that's PHSR and COMA Tier 2. So this was really to simplify whether these regulations are even applicable in the first place. And there's a slightly more zoomed in image of that, which shows that if you had a fleet size of maybe 10 trains, and your average distance you're going to travel those trains is 250 kilometres, you wouldn't have to apply these regulations. And that's the whole point of this, to try and simplify the application of them for industry. There was then a second part to that calculator, which then considered the storage off the train. So storage on train is one thing. You might have significant off-train storage, and this was trying to also factor that in, and you end up with a similar banding. So that was a bit on what the policy team have done with legislation. Then also reviewed all the applicable NTSNs and common safety methods to the UK rail sector, and essentially come to the conclusion that there's not likely to be any significant change in these areas, considering the introduction of hydrogen. Essentially, these apply as they are. There doesn't really need to be a change to them. They should just stand separately. Moving on to some of our industry standards. So these are the standards that's typically published by RSSB. Oh, there's a slight skip there. Essentially, those standards, again, similar to NTSNs and CSMs, they won't change. They need to apply as they are. So things like interior crashworthiness standards, for example, that needs to apply in the context of hydrogen. So you need to still consider that as it is. Moving on to international standards, this is where it gets slightly more complicated. There's a lot of them. If for those unaware of RSSB's work, we work closely with the British Standards Institute and represent BSI on international standards. And we also ask for support from industry to help with that input into international standards. And these are the ones we think were applicable in the context of a hydrogen train. There's 4 there that I've highlighted, which may be of particular relevance. These are the 63341 series of standards. So that comes in 3 parts. The first part is about the technical requirements of a fuel cell on a train. The second part is about a compressed hydrogen storage system on a train. The third part is about testing them and assurance of those systems. The 17268 series will include a part 4, which I'll be chairing, which is about the connector onto the vehicle. So actually about how that interface with the wayside. And then there's the 19880 series standards as well, and 881, which is about fueling stations and fueling containers. And these are all applicable in the hydrogen, from a hydrogen vehicle perspective. And there's a couple of new ones as well that might be coming out too. But this is kind of how the standards landscape will look internationally for hydrogen trains. So there was a bit of a land grab here, I think, from IEC and ISO. So they obviously divided up who's going to be responsible for what. And it seems that IEC are going to be responsible for hydrogen refueling stations, the overarching standard, the 63341 2 series standard and fuel cell systems. And then ISO are responsible for other parts. And you can see how they kind of link together. So on the left side, sort of if you draw a line down from, hasn't got a number yet, but this standard here, this is all off the train. And then the one in the middle is about the connector, and the right-hand side's on the train. So it's trying to divide that up in a sensible way. And from that, you should get a technical picture of the overall train system. So that was a bit on standards. I'll now come on to the part of the work that I was responsible for, which was the system definition. And it's important to define the system so we can make sure we're talking about the right things when we're trying to develop standards. So we used an approach, model-based systems engineering approach to defining the system. So you start with a system at the top, break it down into subsystems. Those subsystems become assemblies, and those assemblies become components. You end up with a good hierarchy of how a system's sort of assembled. It also, the right-hand side shows an image that if you're talking about a subsystem, for example, talk to your supplier, that might be their system or their assembly. So everyone operates at slightly different levels, so it can get quite confusing. It's a bit, it can be a bit daunting to try and actually understand how these pieces fit together, but we try to simplify it as best we can. So in the system definition, we started by just some general assumptions. So for example, the rolling stock complies with all existing legislation. That should be a good assumption to start with. We're talking about gaseous hydrogen, not not liquid or solid state hydrogen. And it's of good quality, and that's particularly important because fuel cells need a particular quality of hydrogen to actually be able to operate. We then set out some very broad environmental conditions. This is essentially worst case scenario for Great Britain, so things like altitude and temperature. So this was just a starting point for a system definition. Then moved on to an ontology. So this was actually assigning every part of the hydrogen system an alphanumeric code. The reason for this was essentially you could end up with, as I've highlighted there, the compressed hydrogen storage module could be on the train or off the train. So it's important to be able to distinguish between those two elements. And so by giving it a unique identifier, in this case FS1, it means it's the on-train part, and would give a different alphanumeric code to the off-train part. So we know we're clearly talking about two different systems. And that's then broken down. So when you see FS there, that's the fuel system. FS1 means the compressed hydrogen storage module is part of that fuel system, and so on. So the onboard storage tank is part of the compressed hydrogen storage module. So it's a breakdown of the components. We then, in plain text, describe the relationship between those components. So we tried to do as best we could anyway. So the compressed hydrogen storage module has inputs from high pressure input from the onboard refueling system, and has outputs to the high pressure to hydrogen handling module, which is part of the fuel cell. So it's trying to describe now, you've got all these parts, what's the relationship between them in a very simple sense. Essentially, this let us come up with a block diagram for the hydrogen system at quite a high level. So this is essentially a subsystem level. So this is below so the system's the train. The train has a hydrogen system on it. This is the fuel system on that train, and it shows the relationship between those different parts. So on here, you can see that the safety monitoring device, for example, sends information to monitoring control, which might be the onboard TCMS system, and that then has a feedback loop which controls the safety monitoring device. So there's a link there, and that's kind of throughout. It's tried to be as simple as possible for those who aren't familiar with model-based systems engineering to be able to interpret this block diagram, and hopefully it's straightforward to read. I will appreciate any feedback on it though. So haven't got much so far. So if anyone's got anything to say about it, please do let me know. That was then done for other modules. So the compressed hydrogen storage module, again, was broken down. And also interfaces to other systems. So in this example, we've got the refueling receptacle there on the left, which is part of the train. It then shows in the red dashed box that there's a connector hose and an accumulator system. This is part of the off-train hydrogen system, and it shows there's an interface there. We haven't really defined it, we just know it exists. So the idea is that someone would define that system, and you should then be able to interface these two system definitions, essentially. A lot of this was actually built on what we call sequence diagrams from industry. So people across industry, such as Tom and others in the room, involved in actually putting together this sequence diagram of a logical chain of events for any sort of process involved in the hydrogen train. This is a process for hydrogen refueling. So it's starting at the top left. It's saying that a service point technician connects an earth cable to the train. They then connect the hose to the train and so on in a logical order. And from that, you can understand the different parts of the train that's interacting with each other and understand those components in the block diagram. So we actually started with a sequence diagram of events and then worked to the block diagram, then updated the sequence diagram and so on. So it was an iterative process to use these models. And that was the system definition, and that again this is all on the RSSB website, so you can go and have a look at that separately. We also then, as part of that system definition, put together a link to the policy work that colleagues in the policy team done. So how the fuel system, the fuel cell, and maybe a combustion engine relates to things like the Health and Safety at Work Act or the noise at work regulations and where might be applicable. And then again, a link to the risk work, which I'm going to come on to now. So colleagues in the risk team, I think one's actually joined online, I think Ben's online anyway, put together a bow tie for hydrogen. So those who aren't familiar with the bow tie process, you have a hazard and a top event. In this case, the hazard was a hydrogen train and the top event was a loss of containment of hydrogen. So that's the thing we didn't want to happen, that top event, that was the big risk. On the left-hand side are all the things that could result in that top event occurring, and in between those what we call threats and the top event, there's a series of prevention barriers. It might not be just one barrier, it might be several barriers. On the right hand side there is a series of consequences, again with mitigation barriers. And what this enables you to do is, without any sort of statistics on these events occurring, because we have no data on this in industry at the moment because hydrogen is a very new subject, it lets you understand broadly the threats and consequences of a hydrogen loss of containment. So looking at the bow tie on the left-hand side, a series of threats were identified, so things like equipment failure, a fueling leak, a system overpressure leading to a deliberate release for a safety reason. That's a loss of containment of hydrogen. On the right-hand side, all the things that can happen as a result of it. So dispersion with no ignition, so that's just the loss of containment. You've got things like detonation, so hopefully I won't have to explain what a detonation is. A jet fire, so a jet fire is a particular risk because quite often with hydrogen, if it's coming at quite a high pressure, the jet flame can be invisible to the naked eye, so it can be quite a big risk. And also things like asphyxiation and fueling hose whip. Fueling hose whip could occur, for example, if you're refueling the train and that hose becomes detached and it's pressurized at 350 bar. That'll then obviously wave around in the air, and who knows what damage that could do. So that was all the kind of threats and consequences that were looked at. And then they went down the route of looking at all the barriers to both of those. So just taking a few examples on the equipment failure side on the left-hand side here. Sorry, it's a bit small for those in the room. Hopefully online you can see it. But you can have mitigation through design and testing, so appropriate design and testing, material and equipment selection, and testing and maintenance might prevent equipment failure. Fueling leak, you can have appropriate fueling procedures and auto shut off. And in all of those threats, there is barriers. So it's just a few shown on screen. On the consequence side, things like a jet fire, mitigation could be things like leak detection or odorant, but there is a problem with odorant because it reduces the quality of the hydrogen. So actually, how do you work that? Supply shutdown and firefighting, which might be a fairly obvious one, but actually it's very difficult to fight a hydrogen fire at high temperatures. So it's looking at how you would reasonably do that. Each of those barriers then goes into quite significant detail. So there's a lot of content there, and I'm not going to read through all of that. So you'll be pleased to know. But it kind of shows the kind of detail that the risk team went into looking at hydrogen events. So that's for one of the threats, and then for the consequences, it was even more comprehensive. Like I said, all this information is available on the RSSB website. I don't believe it's behind a paywall, so you should be able to create a login and find it, and hopefully it's useful to all of you. So in summary, what we're trying to do at RSSB is work with colleagues in industry to actually to better support hydrogen introduction in a safe way, with understanding the risks as well. And with that, I'll pass over to Tom.
Apologise in advance, I'm reaching straight for my water. As you can probably tell, my voice might be limited. I'm hoping it's going to last this long. I need a microphone ultra. Can you hear me at the back? I'll try and fill in a little bit from Darren and his policy, from actually how we've tried to apply it within IMechE realm. I think from the blurb that Toby introduced at the beginning, I think I've kind of broken this into 4 parts, one of which a bit of hydrogen rolling stock context, or at least our view of it, IMechE Rail's journey to embrace hydrogen, as well as some of the safe integration challenges, because I think that's really where we have got challenges for UK. And then a bit of a summary for where those lessons learned have got us in terms of work we're doing, but also where we do see the market, realistic applications and opportunities. Other than my voice, another caveat I'm going to give is the fact that some of this is opinions on an ever-changing environment. I think technologies are changing readily. I think political influence, available money, everything is all constantly changing, and therefore this is our sort of meandering path through it. Giving a bit of context, Darren's already kind of mentioned the TDNS. I think it's a good starting point for where Network Rail foresee electrification going and not going. But I think the summary of that is simply the fact that if we are going to have targets at 2050 for decarbonising and net zero, even earlier in some places, I think we do need to think about this from now going forward, especially when we're looking at assets for 35-year life. And in many cases, it's not just the rolling stock, it's the whole subsystem that supports it. It's really clear that there's a mix of technologies that's necessary, and we need to think about that in advance. I think one thing that's really clear is that battery technologies are available and can fill some of the gaps, but also I think we were fairly early to recognise that hydrogen's got its own properties and its own capability, and therefore there's room for hydrogen in there somewhere. I think also to highlight the fact that, yeah, back in 2020, the TDNS was available, but a year later, UK's hydrogen strategy also was published. And I think within that, it's going back. Within that, it's very useful to acknowledge the fact that rail, I think, pops up 5 or 6 times in various guises. But it's really clear that it was never intended for rail to pioneer the hydrogen economy. It's very much comes with it. And I think the opportunities for hydrogen will come out of the hydrogen economy as it develops. I think it's not just back in 2020, but even now, publications from GBR transition team are actually looking at alternative energy still, possibly for freight, and I'm going to say the slightly harder to do areas of the industry. Another part of the hydrogen rolling stock context is actually the fact that this isn't completely new. We're not completely starting from a standing position. Some suppliers have been developing hydrogen solutions for 10, 15 years almost. And I think it was 2016 that in the bottom left-hand corner there, Island was unveiled in a trans. I think by 2018, it was actually, they suggest it was in passenger service, or at least demonstrating operational capability. And I think since then, we've almost had a steady stream of products and platforms that have been available, maybe two or three even at Intertrans at a time. And therefore, this has been done. I think one thing to note is that there's been a lot of learning from those. The platforms have been developed as they go. Fuel cells have been developed and on second or third generations. But I think at the moment it's fairly unclear of the level of uptake and the successes of those. I think some of it's all shrouded in mystery, where projects that the contracts are signed, but actually how are they getting on? I certainly know that fuel cells at the moment, there's a lot of work still going on the reliability of them, but those things are to be expected with new technology. I think when it comes to the UK, Darren's mentioned a couple of projects that have had a lot of effort and a lot of investment in them. And I think at the moment, we're looking at them very much as experimental solutions for the UK. And I think the real challenge we've got is actually making hydrogen fit into our UK rails. The scale, the infrastructure, the features and culture, ultimately it's integrating it in. I think we do have similarities with mainland Europe and the products available, but we've also got our own nuanced requirements. And whether that's within the depots and maintenance philosophies, competencies, I think we've got to develop across the board. I've almost highlighted there as well, it's not just fuel cells, the four products at the bottom, I think, very fuel cell orientated. ABC, that's the rather large hydrogen engine in the middle. Actually, some of our Evershot employees have gone out to visit some of the engine manufacturers there to have a look at, then they'd be transplanted into a freight locomotive. And I think it was the latest Stadler RS0 rail bus this year at Intertrans, where they had both a fuel cell and an internal combustion engine option available. And that was partly packaging. If you can have a compact package, you've got a slightly less efficiency, but you've got more room for storage. In terms of our journey to embrace hydrogen, it very much started with the where and when. Again, taking the TDNS map as an example, I think Darren's mentioned a few of the areas. Really, this was about what's the right product for the biggest reach. We can come up with one solution, but we know there's trains come in all shapes and sizes for different applications, and actually where is best to approach them. Really, I think this was triggered by operators approaching us to say, what have you got that can replace diesel? Because we don't want to maybe not order diesels now, or we've got an aging fleet of trains. But also, some of it is based on actually how do we make a fleet that could be a critical mass, that actually you can order enough of them that actually makes sense. I think we all established the fact that if you're only going to order 3 or 4 trains for a tiny little route, it's actually economically not so viable. Also, I think it was a lot of acknowledgement that we may not just be looking at the rolling stock. It's about making it supportable, especially in the early days. It's almost like a full logistics support program where you need to be able to think about how the refueling is going to take place, the consistency of that fueling, as well as the fleet support. I think one thing we realised as well, got to keep things simple, especially in the early days. A lot of it was making sure that whatever product we came up with had to align with the UK's government wider objectives. So in terms of product, first product placement picture, the Class 600 Breeze concept. So this was actually taking our existing learning from a Class 321 fleet, where we had actually undertaken quite extensive work, looking at detailed refurbishments, retractioning, putting HVAC in, and actually we had a really good understanding of that particular product, what it's capable of doing, as well as having a partnership with Alstom. Now, this was early days around 2018, but Alstom's Corradio Island experience was really showing the fact that actually this could be done. They've already learned a lot of lessons. Actually, the path to coming up with a sensible product was to be able to combine the two product, where we've actually got a good understanding of integrating into it, but also using Alstom's engineering teams and capabilities to bring that together. So that journey started basically in 2018. Alstom, on our behalf, undertook a fairly detailed feasibility study, and actually that it stopped and started, but ultimately in 2020 it came a time when actually we reignited that based on Northern's interest for a number of their routes that they were looking at, and really we worked towards actually coming up with an offer of what it would take, and actually undertaking more detailed designs on that feasibility to really work out actually the technical details and learn a bit more about how we can bring this to reality. I think one thing to note on this particular slide, lovely timeline, but as you'll know, we've kind of passed by the date when we might even have part of a fleet available. I can say that actually this project pivoted somewhat in the middle because of lessons learned we did from the first design review phase. Moving on. Here we go. So how will we create it? Well, ultimately, it was a 4-car 321. And actually, how do we turn that into replacing ultimately or a product that can viably place a sort of 2-car 15X diesel train? Well, really, it was a matter of removing an unnecessary vehicle, a trailer, bringing those two together, replacing the traction equipment, as we've done in the past. So new auxiliary converter, new traction converters, new traction motors. Ultimately, the hydrogen elements were going to be in the driving cars. So our concept originally was onboard hydrogen storage. So this was 350 bar cylinders taking up the leading end of the driving cars with the fuel cells at the number 2 ends of those. And by this, with an internal refurbishment to actually make sure that we were looking at uplifting the entire train in terms of performance and visuals and comfort, that would then give us equivalent number of seats and equivalent capability as a 2-car DMU. The only difference is we've got a lot more axles and it's a bit heavier. So going more into the detail of that, this was more the phase 1 advanced works. Really, this exercise was very much taking that original concept and actually working out how this can be done in reality and what compromises will be made. And I think this was really the engine room of development, in that taking the product with our understanding of a class 321 car body and actually working out how does the packaging really work? What are the priorities around it? It's the packaging in terms of constraint. So how many tanks? Which orientation? How do you minimize the pipework? How do you minimize the number of fittings that could leak? How do you make sure the ventilation works best for you? So a lot of work around that. Ultimately, we wanted to make sure that the process we were going through was really sensible. So we weren't necessarily taking liberties or being cavalier about it. But actually, we did look, as you can see from some of the diagrams here, the fuel cells were at the number 2 end originally in the feasibility. And actually, we looked at saying, actually, we lose so much headspace in the saloon. How do we bring that forward? What's it look like when we do put that, for instance, above the storage? So by moving these building blocks around, it was very much an understanding to say actually what's sensible, and ultimately trying to work out what our fundamental approach to safety was. We didn't want to compromise safety in all of this, especially with some of the areas that Darren's highlighted there. I think it was a very steep learning curve. I can see that we challenged ourselves a lot in terms of the packaging, especially with the UK loading gauge, constraining everything together. And we never took off our mind the need for the approvals and validation strategy. So very much focusing on how we could actually get a viable product, not just for an experimental concept and demonstration, but actually something that could run in service. In terms of the train scope and functionality, because we're looking at replacing a 15X, we were looking at capability of performance, so 90 miles an hour, accelerate equivalent to what we were replacing. And really for that, we were looking at a 350 bar storage pressure. We're looking at around 300 kilograms of usable hydrogen for the first phases. That number varied a lot during our packaging work. So we jumped up to 350 down to 285, but it was constantly being evolved. Ultimately, we were looking at 440 kilowatts of fuel cell. And in terms of battery, I think I put there 2 batteries with 150 kilowatt hours total capacity. Ultimately, that was 3.8 tons of battery. This was, you say hydrogen train, this was a battery train with fuel cell feeding that. It was very much cramming an awful lot of stored energy on board. And that's why we really had to take it seriously from a safety and risk management perspective. Other things we did in terms of performance was very much looking at matching performance. So it wasn't just the concept and packaging, it was actually how would this thing accelerate? What would it look like in terms of meeting diagrams, timetables, etc. And actually, fuel cells also have a degradation to them, as do batteries. So you've got end of life effects to take into account. So all of that had to be factored in to make sure we've got sufficient headroom to be a usable product at the end of the day. I say this is the pivot moment. I think in working so much on what it would take to convert an older train, I think we learned so much in the process that actually we realized that we were constrained a lot by the older train in terms of the structure, the loadings, and really, I think we established the fact that where would we want to put the fuel storage would be on the roof if we could. And I think this is where we had lots of internal debates and challenges from a risk assessment perspective of, are we doing the right thing? I think there's a number of other inputs in there. I think our chief engineer said we had a 1 to 5 categorization of projects, where 5 is a new build or fairly the largest category. And he said this is a 7. And I think, yeah, we all realized that what we were trying to do here was a huge undertaking, and the timescales would be lengthy. I think you saw the time plan was like 6 years, but actually this would be a challenge to deliver that within the timescale. I think what we also realized was that lots of the fundamental risk management principles around that are available in modern trains, such as running capability, the ability to keep going in failed states so you don't get stuck somewhere, was actually really important, especially when considering tunnels or enclosed spaces. And so some of the things we would get from a new build train were very difficult to build into an old one. And that meant already we were looking at changing the braking system, considering, do we put a TMS system on board in some shape or form? And very quickly, a simple modification for hydrogen equipment turns into a whole-scale rebuild. And therefore, actually, the phase 2 part of the project was no longer looking at the class 321, which I can say some of them unfortunately have now gone to the scrap heap and being recycled, repurposed. And instead, we worked with Alstom based on a new concept, a new train. So starting a little bit more fresh, but at the same time, this was incorporating our lessons learned and our knowledge that we'd built up from those earlier concepts into it. We also wanted to make sure that we had more detail regarding the operability of the train. So very much linking what it's going to be, what it's capable of doing needs to very much reflect how it's going to be used. So with that, safe integration challenges, I think Darren's kind of highlighted bow tie analysis and its use as a risk assessment tool. I think lots of the design decisions we made, it's a bit of a lesson learned, was based on realizing how grueling the risk assessment is for new novel technologies. I think when we looked at it from a CSM and risk register perspective, I think the first pass we did 1,400 line items of risks to be managed, and very quickly these things escalate, especially when it's very easy to escalate and catastrophize, such that every risk you've got ends up in a detonation, using the word that Darren used earlier. So we actually approached it from a top-down and a bottom-up approach to make sure we've considered it from almost like a FAMICA from the bottom up, but from the top down, very much using the bow tie model, which is very useful. Oil and gas pioneered that, and it's very useful for new novel technologies. And by doing this, it helps to develop our internal maturity from a hydrogen perspective, and actually what's important, and break down actually what are the key safety principles we're trying to apply. With this new platform and safe integration, dare I say, although this is still conceptual, it was very much based on the fact that actually the buoyancy of hydrogen does make it an advantage that if it does leak, if you can give it open air, if you can put it on the roof, it's massively beneficial. So previously with these ideas of fuel cells sitting above storage with forced ventilation systems, it all works on paper, but actually you're relying on lots of systems working together, and just added complexity. Keeping it simple was a real advantage. I think also we've found the constrained packaging means that access for maintenance is really challenging. And also, I'm going to say, it goes against the rules basically for high pressure gases. If you do contain them, although it's going to be beneficial from a leak detection perspective, if you can sniff it out, at the same time, actually it can be very much detrimental if you did have a leak that you couldn't control. And so therefore, giving it access to free space and open air was seen as a major requirement and a driver for going for new build. Also, some of the benefits of going for new build was making it scalable. Ideally, we wanted to be able to say, if we've got the same battery, fuel cells, and equipment on each vehicle, ideally we've got better redundancy. We can have almost consistent designs that are just replicated on each vehicle, rather than going for very disparately different ends. And ultimately, by going for a new build platform, you can automatically adopt the best practices for crashworthiness, fire compliance, and I said running capability was a real requirement. Especially our older train, which we were looking at there, had energized to release brakes, when actually modern day trains have energized to apply brakes. And that philosophy really backs the ideas of running capability. And we just don't get that unless we put in a state-of-the-art brake system on the Class 321, which wasn't what we originally had experience in doing. I think one other point is that they also come with a mature and reasonably reliable TCMS system on board. And that's one thing we didn't have. And I think retrospectively applying that is an enormous project in itself to an ultra train. Safe integration, I've kind of mentioned a lot. I think the few things from this slide in particular I wanted to get across was that actually undertaking a hydrogen project is actually quite a responsibility, given the risks in the industry. It's the last thing we wanted to do was be a bit cavalier, and suddenly the industry says, you don't want to do that, or an accident happened, you don't want to do that, and kill off the opportunities for future, or for anyone else attempting it, to be honest. We wanted to take it very seriously. And with that, it was felt really important to make sure we got the documentation right. And we did definitely make sure that the concept of operations for a hydrogen train very much marry up with the safety concepts around it, why it's built the way it is. And I think one thing throughout the project, we realized that there were a lot of different opinions about hydrogen coming from all sorts of areas. And actually, there's a lot of stakeholders that need to get on board, especially when you're talking about not just a train, but the entire railway system. And therefore we found, I'm going to say right in the middle in red, there seem to be multiple opportunities to unhinge or discredit an HMU-owned special conversion project. And I think from there, that's when we realized actually we need to make sure the documentation is tight and that we do make sure there's no gaps in the way that we manage all the stakeholders and all the design and development and make sure it's robust. We actually came up with a principles and some very high level safety philosophy for how we could describe, say, on one side of A4, why hydrogen train could be done safely. And that's actually something we've taken forward with future projects. Also, I think a big realization is the fact that when we buy new trains, quite often they're from manufacturers, that's what they do. They have a long line of history of using common components or an approach to things, and therefore their hazard record and the way they apply CSM is quite mature in that they've got one that they can dust off, link it together. And I'm not saying it's done at the end in a rush, but actually a large amount of it is based on past experience, meeting standards and codes of practice, and ultimately reference systems that they've actually got experience of themselves. When you look at hydrogen, we haven't got a reference system to rely on. It is fairly novel. And also, Darren, I think as you were saying, the codes of practice don't really exist for doing exactly this. And therefore, we're going straight back to explicit risk estimation. And therefore, one thing that was really apparent was that the CSM process actually needs to start even before you've drawn anything. Some of those experiments for packaging, moving things around, was a necessity. It wasn't wasted effort in a concept that never was. And I think that's going to be the case for any train, whether it was new or old. The fact that actually this whole CSM loop needs to continually go through right from the beginning conceptual stage right the way to the end. And actually realistically, when we look at new build train and say, how do we get this into the market within 2-3 years, perhaps? Sometimes these ambitious targets do exist from the outset. Realistically, I think from hydrogen, we're probably not too far away from what we originally thought. It will take about 6 years. That's not de facto. Someone might do it already in 2, but I think our expectation was that to build it and to get the knowledge in place and bring all the stakeholders together, it will take a considerable amount of time. Also, validation. I think Darren, you highlighted again, hydrogen gas is an interesting thing, especially at high pressures that we're not used to in the rail industry. I think at the end of the day, a really important factor was validation. We don't actually know. We've got ideas of what a leak would look like or what it would do, but actually getting a company that specializes in CFD and explosion simulations was really useful in terms of actually what's our reasonably foreseeable leakage circumstances, and actually what would that look like, especially talk about the far north lines in Scotland. Let's get Inverness station. It's got similar proportions to a depot shed. It could actually be quite relevant to applications. Actually, let's see what a TPRD, a thermal release, pressure release device, what would that look like? Similarly, if we had a small leak in a gas cloud on a quiet day, how big could the cloud get with the ventilation in a depot? And therefore, that was really useful in actually driving an understanding for actually what's the consequence of one of these events? How big could it be? And actually that then feeds back into our assumptions about the requirements of the vehicle, how to be technically tight. We can't afford a leak. Let's not even get there in the first place by design. And similarly, this was a case of actually we got a D gauge to go and have a look at some tunnels to actually say what size tunnels are we actually looking at here for the far north lines, and therefore that way we could take those simulations and say if we got stuck in a tunnel, what would the progression of a dispersion cloud look like? And in some ways inform us, actually, at what speed does it become not an issue? What are we up to now? This slide did have I'm going to ask you to use your imagination. This slide did have a lovely picture of a locomotive. Nick, who's the lead today, is working very hard on the project. And I think although we've had a press release back in the summer relating to it, all I can say is that this locomotive actually, it's very much similar to the earlier drawings, full of cylinders, filled not quite to the rafters, but a large number of hydrogen cylinders on board. It's also got a steam turbine in it. So it's a little bit novel, but at the same time, I'm going to say watch this space, because there will be something at some point we can actually present into that. And it is exciting. It's not the fact that what are we up to now, just a blank page of nothing. Also, in the Greater Anglia area, we're having a bit of a study that Arup are helping us with. And in particular, this is from past learning as well, in the fact that it's not just about the train, it's about looking at all the things coming together. The stars almost have to align here, in the fact that actually it needs to be the right kind of infrastructure. What's the performance of the train? How can it be maintained? And actually looking at everything together on the same level, not just designing the product and saying that the customers will come, but it's actually almost making sure that all of the steps in terms of, is this safe? Is it suitable? Making sure that the operations and maintenance planned can actually look after a vehicle, and making sure ultimately economic viability is there. So bringing all this together. And this has now, I suppose, influenced our approach looking at hydrogen opportunities going forward. It's not just the product, it's the system around it. Bringing this to a close, because sorry, I've blown the time budget completely. I think a few questions about where the market now exists and what we've learned. I think very much when we looked at the original map and we said, oh, there's huge opportunities. 1.5x fleets, they were everywhere. This is hundreds of vehicles, loads of opportunity. I think now we're very much saying we can see pockets of opportunity, but nothing major scale at the moment. I think things will come in time. A lot of it's going to be driven by price, cost. I think when we've looked at hydrogen cost, not only is the technology expensive in itself, putting it into a vehicle, which is, I'm going to say new build now, is more expensive than it has been in the past. And I think the industry really to get over that challenge, the fuel price has to be cheap, has to be good. And I think hydrogen, I'm going to say it's not just rail, it's all industries with hydrogen are kind of waiting and watching to see what's happening with fuel prices. And I think until offshore wind is almost doubled again from what it is, and suddenly we've got wind farms generating almost excessive electricity to what we can use on certain days, and that's used almost like a storage of hydrogen. Until those days come, I think the fuel prices are going to remain high, and it's going to have to be, I'm going to say, politically driven to make the step changes to actually have hydrogen in any capacity. But I think there are projects out there. I'm going to say no projects have really taken off. We haven't seen massive success stories waved around, but it's out there and it's happening. I think the opportunities are there. And I think at the end of the day, it's not just about comparison with diesel. We're very quick to say, if we want to replace a train in the far north lines, we're kind of comparing the costs with diesel. And at some point, I'm going to say, if we ask that question inwardly, would we buy a fleet of diesel trains today? I think we would be hard pressed to convince everybody and all the stakeholders that that's the right thing to do. And I would say in a few years' time, I think we might be even saying the same thing about a bi-mode train with diesel as a power source. So realistically, we've actually got to make some of these decisions. We've got to think about it. And I think although these exercises at the moment we haven't got fleets of them out there yet. I think one thing that we have learned internally as Evershot is we're far better prepared for when the opportunity does arrive. I think we know enough to be in a good position to challenge design reviews and be part of the new build projects and be able to be informed buyers going forward. And I think the opportunities will arise. But, it's taking longer than we expected, but it will happen. Thank you very much.
Very bad beats. It will give Tom's voice light rest, but not only we get the opportunity to have two great presentations, but an opportunity to ask a few questions. So if you don't mind coming back up to the lectern, just so we can see you on the camera. Is there anyone in the room that would like to have the first question? Well, okay. Well, we've definitely had some questions come in over the chat. I'll try and find one that's not for Tom. Yeah, so this is probably one, I think, Darren, that you can take. It relates to the safety bow tie risk modelling. Obviously, couldn't quite see everything that was on your diagram, but I'm sure it looked incredibly thorough. But one question from Richard was about whether terrorism had been considered.
I think I saw that pop up. Yeah, that's a really interesting question. I don't think we considered it in the project because essentially terrorism is a risk anyway. And when you're considering hydrogen, you've got to consider all the things that could already impact the rail industry, and terrorism is already one of those. So that wasn't really bespoke to the project. It wasn't a specific risk around hydrogen. Terrorism is a general risk. It should be considered in that way, much as all the standards should be considered as they are. So hopefully that doesn't model up to that, but yeah, that would be my answer to it.
No, thank you.
I think if I just add to that, I think from a product design and specification perspective, we very much wanted to make sure that when we've got hydrogen tanks on a roof, for instance, that standing on a bridge parapet and chucking a concrete block on over the edge would be not a viable source. So I think when it comes to terrorism, it depends on what level of, is it just vandalism? Is it something more severe? Another area in particular was cybersecurity. So when we've got so much onboard energy storage, is there more potential, especially more interconnected systems and integration? Is there more potential for someone remotely switching off a safety system that's there in the background monitoring a leak, for instance? Or is there any valve that, for instance, could be tripped in order to cause a severe incident? And I think that's definitely something that needs to be considered in the requirements now. I think it ultimately is a problem with onboard energy storage. You have so much more potential.
Thank you. So there's a couple of questions I saw in the chat around the design. I think it was probably the first concept you showed. So in terms of the hydrogen storage tanks, the question was around why we put them within the saloon of the vehicle rather than underneath or on top, because you're losing the space within for passengers, and there's a question around why we're working at 350 bar. I don't know if you've got any question.
Yeah. Okay, so I'll do the pressure one first. 350 bar is fairly common for industrial applications. Hydrogen. Automotive is looking at 700 bar. It doesn't give you twice the capacity, interestingly, but it gives you a lot more available energy for the space you've got. But 700 bar, similarly, with consequences, is that much higher. So looking at the volumes we've got, buses, for instance, use a 350 bar system. And therefore, it's almost standardization in what tanks are designed and tested to typically, and also the componentry. Because we didn't want to it doesn't make sense to come up with a sort of a bespoke pressure. I think when it comes to tank storage, there's actually a surprising volume of hydrogen required. Underframe isn't necessarily always ideal, given ballast strikes, and it's a pretty harsh environment underneath the vehicle. The roof is the ideal. I think we've established that from buses typically. Hydrogen buses typically use tanks all lined up on the roof, and sometimes towards the back end vertically. And that was, given a choice, that's where we would go. Looking at the original vehicle structure, if you're going to cut a roof off and lower the ceiling, which was already very compromised, it just didn't work for us. Starting with a new platform, you can lower the floor slightly, you can make some of those provisions, but looking at Class 321, we would effectively be walking around underneath a very low ceiling height, and also you would structurally really need to think again, and you're almost rebuilding and redesigning the vehicle structure, and that's not what we wanted to go.
Just on the pressure the question, and sort of linking to what Tom was saying, a lot of what's going on in the standards world is looking at other sectors and actually saying that's what they're doing. automotive or heavy goods vehicles, this is what you do extra for rail. So it's not doing anything unique, because actually that would have a cost associated with it. So it's looking at, okay, what do they do? Okay, we'll just adapt that for our needs. So that's what the standards are kind of based on.
I can see we've got a hand up online. So John, I don't know if you can unmute your mic and ask a question, and if in the room you can think of a question, we'll come to the room next.
Thank you very much. Evening, everybody. So my question was sort of around fire extinguishing systems, and would you recommend or specify in the standards a specific fire extinguishing system for hydrogen trains? I think we've all worked on a variety of rolling stock, and there is a variety, isn't there? AFFF, water, energy and gas on HST. So did you consider that?
So from a standards perspective, we did consider it. We sort of looked for the work we were doing. We were looking at, could you reasonably suppress a hydrogen fire because of the temperatures involved and the pressures? I don't know if that's something that we would specify, or actually look at other sectors again, look at what they're doing. I know that it's very, very difficult to extinguish a hydrogen fire, especially a jet flame. I know the emergency services have certain ways that they deal with it, and we have engaged with emergency services to see what they do. I think from a standards perspective, it'd be quite a difficult thing to set out, because it might be unique to the design of the vehicle. So actually putting something in a standard might be limiting, actually, from a perspective of the design of the train. Don't know if, Tom, you have anything to...
Yeah, I think from the vehicle interiors perspective, where fire extinguishers are normally located to put out an interiors fire, something that's happened, newspapers, etc., I think that would be no different. From a hydrogen perspective, as Darren said, the energy levels and the temperatures are extremely high. And also, if you had a leak that was providing a jet flame, I think generally you would advise people not to try and tackle it, but to actually a full-on sort of emergency evacuation type approach. But also, one thing we did look at was, if you could extinguish it, there is a reasonable potential that now you've got a build-up of explosive gas instead, which might be far worse than letting the jet flame do its thing. And I suppose in many ways it's more of a discussion really for actually how much damage it could do to the asset. Are you looking at a jet fire actually becoming an insurance issue more than anything else? I think from a safety perspective, ultimately you want to avoid the incident happening in the first place as far as possible. And then if it does happen, you make sure that you've got good procedures to evacuate and manage the situation without necessarily putting anyone at risk.
Yeah, sounds very similar to the challenges we all have with lithium-ion batteries. But, yeah, thank you for that.
The one thing I'll just add on that is that in looking at hydrogen escape, it's important to realise that the oil and gas industry and other industries, you don't always realise where there's a hydrogen fire. It might sound a bit peculiar, but it's not visible to the naked eye, typically a jet flame fire. So, for example, I think oil and gas tend to use a combination of sort of thermal imaging arrays, because some thermal imaging cameras aren't at the right level to actually pick up that high heat, and also using ultrasonic detectors to pick up that initial high pressure escape, which you can't hear. So it depends on the environment as well, about actually whether you can even detect that there's been a leak or a fire. So it's quite a complicated subject, unfortunately.
Okay, thank you. Any questions in the room? Yeah, we've got one from Chris.
Yeah, I mean, you mentioned that the main thing stopping hydrogen at the moment is the money, if you like, or it seems to be. In the mainline rail industry, if the money bit was sorted out, is there anything else that would stop you implementing it? There's a lot of safety things that you've talked about. Clearly, that's what it's all about. And there's nobody saying you just can't do this. But I'm thinking, on London Underground, it might be a different story. For example, long tunnels. Are there any routes where you say, no way, you can get it on that route because there's a great big long tunnel that wouldn't be safe, or anything else that would stop you absolutely?
I think you're absolutely right. Money is a factor, but I think if the right motivation's in place, that can be overlooked to some extent. I think one of the main issues is finding the right place for it. So as I said, we start off with a big map going, this is a new go anywhere opportunity, and actually realistically, it comes down quite a lot. One thing we've looked at, especially in the Greater Anglia area, is it's beneficial because it's relatively flat. It's quite easy to model the sort of the right distances. You can actually carry less hydrogen to go further, which is a great benefit. But also, ultimately, do you want to run hydrogen trains under lots of electrification, for instance, where you've got 25 kilovolts and arcing damage could be a massive risk factor in itself? There is a right place for hydrogen, and you're right, it's not long tunnels in highly built up enclosed areas where a leak could be devastating. But there's some areas where, for instance, we looked at risk assessments which included nearby hospitals with big air inlets and filters and all the rest of it. The last thing you want to do is have a building ingest the hydrogen from a leak. You don't want to go there. So it's about doing the right assessment across the patch and actually working out, is this appropriate technology? And I think this is why there are pockets where it is suitable. I think I'm trying not to sort of kill off hydrogen in some respects. Quite often the best routes for it tend to be in wide open, looking at far north lines, for instance, wide open spaces where there are some tunnels, but actually there aren't electric lines and things in them. Actually, the risks look manageable. I think the problem is that they tend to be relatively economically limited in terms of they don't carry many passengers, and they already have a lot of subsidy to operate them in the first place. So suddenly putting your very high value asset to take out diesel in that respect doesn't make sense, especially the fact that actually running in clear open countryside, one of the benefits of what we're trying to do, although decarbonisation is really important for us, actually one of the main drivers to get diesel away from enclosed spaces, burning in New Street, for instance, is about particulates and emissions from inhalation. So in the middle of the countryside, when you've got a diesel train, is that really the first train we want to replace with hydrogen? I think yes, from a safety and feasibility perspective, but viability seems to be the opposite end of the scale. So I think this is where we've got challenges, is finding the right combination of actually bang for buck and benefit overall.
And just from my perspective, I think that internationally there's always been a bit of a concern with using hydrogen. Dare I mention Hindenburg? Someone's going to mention it at some point. But as soon as you mention it, everyone immediately goes, "Oh, Hindenburg, that was a bad thing, wasn't it?" It just potentially, that was a long time ago. And hydrogen is safe if it's managed correctly, and that's what we're trying to demonstrate through the work we do. So it's about managing those events. There was some pre-normative research done in Europe called High Tunnel, which is looking at hydrogen in tunnels and confined spaces. And some of that work, which was done by the HSC over here, was directly applicable to rail. So they purposely detonated some hydrogen in a tunnel with some very interesting results. But yeah, you could kind of see the damage that it could cause, but we now have a greater understanding of those risks. I think it's about just managing those risks. So I think if the commercial problem wasn't there, it's just about actually looking at safely managing it and looking at things like where you put your tanks on the train, things like thermal pressure release devices. There's Ulster University are working on new tank technology as well, which might remove the need for a TPRD because some people don't like them. So it's actually looking at other ways to manage these risks as well. So there's quite a lot going on to manage safe integration of hydrogen.
Okay.
Yeah, hi, Stephen Neal from Unitrove. I guess it's a bit of a follow-up question, really. I guess there are going to be other kind of alternatives, battery electric and things like that. So where do you really feel that hydrogen comes into its own? Like, what are the kind of use cases do you think that hydrogen can win out over some of these other future-looking options? Would it be something like range, for example, or is it there just areas where electrification is very difficult? Where do you feel and see the challenges of that?
So looking at non-electrified routes, which is typically where this is going to go, it is one of the main constraints is range. If you look at batteries right now, they have a very limited range. Before you have to charge them, you have to put some infrastructure in and get them back. So who knows, if you could get better range out of batteries, that might make it a harder decision to make when it comes to actually employing hydrogen. But similarly, you've got to think about actually that charging infrastructure. Where's that going to get power from? How are you going to manage that? So it's not just about the ranges in the battery. Have you got, again, the supporting infrastructure to support that battery? In terms of looking at what RIA have done, they mention hydrogen in their report, so you can see they'll have a place, and it tends to be those kind of rural areas which aren't really, you can't really build the business case to electrify right now, and there has to be an alternative to diesel. So it's always given as an option. I don't think it's possible to say absolutely, from my perspective anyway, where hydrogen could be used, but I think it absolutely does have a place somewhere, and I suspect that somewhere will have a hydrogen train at some point. I don't think it's something that's just not going to happen. And also, there's the use case that so you've got passenger and freight, but also not forgetting things like yellow machines. So the on-track plant and on-track machines, they're all typically diesel. So actually, you could use hydrogen combustion engines there. That could be a smart way for them to decarbonise. So, anything to add?
I'm going to build very much on what we said, Darren. I think one of the examples, for instance, is hydrogen buses, where actually battery buses can't perform a full day's service. They just can't get there, and actually their downtime is considerably impaired by the time taken to charge them in a sensible way. Yes, you can fast charge the battery, but it's detrimental to the battery life, which are high cost, high value items. But at the same time, actually, you need a huge amount of stored energy to charge them rapidly, and actually that often isn't available. And therefore, I think hydrogen has its place because it can give the range, not as much as a tank of diesel. It's been a bit of a gift, to be honest, in terms of the calorific value of it. But hydrogen actually gives you the opportunity for relatively fast refueling. It's not super quick, but it's comparable. And a train can go out and do a full day's service before needing to come in and be refueled, for instance. And therefore, it actually tends to fit today with today's technology. And future fuel cells are getting more efficient. In the same way, batteries are catching up in an automotive sense. But actually, when we're looking at the stored energy battery sizes required for trains or locomotives, it's still got a long way to go. And I think we've also established the fact that batteries are volatile in their own sense as well. And so I think, although our hydrogen concepts very much have battery storage, I think hydrogen actually, I think, has more potential when we look at things where the energy levels are too much for battery, realistically. So I do see a space for freight and maybe even high-speed rail where there isn't electrification. And that might not be in the UK, because there's lots of countries out there which don't have a standardized electrical systems in terms of overhead lines. They will be starting straight from a 100% diesel network to something else. And I think that's where hydrogen really has the potential.
Thank you so much. I'm conscious of time, but thank you very much for answering those questions. Perhaps I suggest we might be able to do some of the ones online via correspondence, and there might be an opportunity after for people in the room to grab our speakers in the event tonight. So yeah, I think what we really need to do is just to one more time give Darren and Tom a really big round of applause to thank them.
Hold